everyone. Here is chapter 10, Systems of Equations and Inequalities. And we don't do every section in this book, so we are going to, from this chapter. So we're going to start with section 10.2, which is Systems of Linear Equations and Several Variables. Now I am going to start with a system of two equations and two variables. So understand that to get a unique solution to a system, you need to have the same number of variables as you do equations. So if you have two variables, like in this case, we have x and y, you do need to have two equations in order to get a unique solution. So in terms of solving this system, hopefully it is something that you remember from back in algebra, but we have two equations, like I said. There are two different ways to solve this. You could use substitution or you could use elimination, and both of them are going to give you the same answer. There is only one solution to this system, so substitution. So with substitution, what we're going to do is we are going to solve one of the equations for one variable. Notice you have a couple options there, but if I take equation 2, as you can see, I can very easily solve it for x just by adding 3y to both sides. So this tells me that x equals 3y minus 1. Now that means that that's the relationship between x and y. So then I can take equation 2 and I can substitute it into equation 1 where I see x. So now in equation 1 we have 2x plus y equals 5. But instead of writing x, I'm going to write what x is equal to based on equation number 2 and write 3y minus 1. And I was going to do that in blue, but for some reason it didn't want to be blue. So here we go again. So we take that 3y minus 1 and that's going to go here. Now notice that the key thing is that what happens is now we have one equation here that only has one variable. And that allows us to solve for the variable that we're looking for. And then, of course, solve for the other one. So I'm going to use the distributive property. You are welcome at this point, if you've been writing this down, to go ahead and solve this for y. Just get a little practice there. And, you can make it more or less steps. But we do end up with the idea that y equals 1. And you're not done because this is a system of equations with x and y, so we need to get x as well. But we know what x is back from the top. We know that x is 3y minus 1. So if we take 3 times our y that we just found and subtract 1, we find that x equals 2. Now that is a point. That is the point 2, 1. Meaning that if you place 2 in for x and 1 in for y into both of those equations, both sides will be true. And that's what makes it the solution. Now another way to solve this would have been using the elimination method, and I'll show that as well because both work. With the elimination method, you want to typically multiply one of the equations by a number, a constant, that's going to get multiplied by each piece, and which is going to allow you to eliminate one of the variables to allow you to solve for the other, and then back substitute to get back the variable that you eliminated. So we notice that we have 2x plus y equals negative 5, and we have x minus 3y equals negative 1. There are multiple ways to go about this. So what I'm going to do is I'm going to take equation number 2. Maybe I'll write it here. So I'm going to take equation 1 and I'm going to add to that negative 2 times equation number 2. So what that means is I have equation 1 there. This is equation 1. Now I'm going to take equation 2 and I'm going to multiply each piece by negative 2. So I'll have negative 2x plus 6y equals 2. So each of those pieces got multiplied by negative 2. Now what I'm going to do is I'm going to add the two equations together. Notice that eliminates the x, and it gives me 7y equals 7. Well, look at that. We've seen that before. That leads me to y equals 1. And then, of course, Now the idea would be that I could put this y equaling 1 in either equation that I have. So let me, in order to solve for x, I can do 2x plus y, but we know y is 1, equals 5. So this, of course, is my equation number 1 here. I subtract 1, I divide by 2, and I have x equals 2. So of course, same answer, 2 comma 1. Whether I use substitution or elimination, the answer is still the same. So now we have an example. We're being asked to solve. We have 3 equations and we have 3 variables. This is what will allow us to have a unique solution. But I want you to notice the style of these equations here. And you might notice that the first equation has 3 variables in it. The second equation only has 2, and the third only has 1. And by the shape I just made, you might be able to guess that this is called triangular form. And what that simply means is it's in the shape of a triangle, and because it has 3 variables, then 2 variables, then 1 variable, it allows us to then solve for our 3 variables fairly easily. So we have 3 equations here, 2, 3. You can see that with equation number 3, I have 2z equals 4, where very quickly I can see that z equals 2. So now I have one of the solutions to this system of equations. Now, with equation 2, I'm going to use the fact that I just solved for z. So we have y plus 3z, but we know what z is. We just found that. Now this is allowing us to then solve for y. So now we have 2 of our variables for this system of equations. And now we just need to solve for x. Now I need to go to equation number 1. So notice I'm using that back substitution, going up and up, to get my previous, these other equations, to get that last variable. So I need to solve for x, but we know y and z. So now we have x plus 2y, but we know y. And we have minus z, but we know z. So I'll plug those values in. Now I have an equation of 1 variable. Notice it's just x, and then some numbers that I can combine. You're welcome to pause and finish this. Adding 8 will give us x equals 4. Now this is written as 4 comma negative 3 comma 2. It is a point, x, y, z. You can think of it on the 3-dimensional planes. And this is the value that makes all 3 of these equations true. It is the only value that does so. But notice it really helped that we were in triangular form. So when you're able to put something into triangular form, a system of equations, typically when they have more than just the 1 variable, 2 variable, 3 variable, when maybe all of them have 3 variables, your goal is to write that into triangular form and then use the back substitution. That's all I did in the last example was back substitution. And the whole process of this, writing into triangular form using back substitution, is what's called Gaussian elimination, from a famous mathematician named last name Gauss. There are 3 things that you can do that to any of the equations to try to get it in triangular form that will always give you the equivalent system, meaning the solution stays the same as long as you stick to these 3 things. So you can take 2 equations and you can switch them. If that helps you, you can put one above, switch them around, it's no problem. You can take, and I did this in the first example, you can take, using the elimination method, you can multiply any equation by a non-zero constant. So if it helps me to multiply any of the equations by a number, positive or negative, as long as I multiply each term in that equation by that number, I'm still good to go. No problem. My solution will still be the same. You can also take an equation, multiply it by something, and then add it to another equation. And that's really helpful for eliminating the variables that we need to eliminate to get ourselves into triangular form. So that's another option that we have, and that we'll be doing, that you'll see today. So let's take a look at an example. All right, so notice these take some steps. I'll try to write it out in the most cohesive way possible to help you. So we have 3 equations here, 3 variables. And what I might do, I'll be doing with these types of systems, because it's kind of helpful, is I'll be calling this row 1, row 2, row 3. So I'm using a little subscript there, and that will just help me keep track of what I'm doing. And then when I use my numbers, that will help me kind of know which steps I'm using. So the idea here is, and I'll erase this, but we want to try to, get ourselves to this idea, this triangular form. So we'd like to eliminate y and x from here. We'd like to eliminate x from here. If we can do that, we end up using our Gaussian elimination, we will end up with an equivalent system, and we'll be able to solve using the back substitution. That's our goal here. So because all of these start with x, and 2 of them have just a y, it's our first one, we have a lot of options here for what we want to do. So we'll just kind of maybe keep it, more as straightforward as possible. So the first thing I'm going to do, my first step is, like I said, I want to start off by eliminating this x. And so there's a couple different ways to do that using what we're allowed to do. I'm going to take row 1, I'm going to add a negative row 3. So what that does, notice, it's going to give me negative x, negative y, negative 4z, positive 3. And then I'm going to add that to my row 1. And what that will do is eliminate the x in row 3. Okay, so taking a look at this, I'm going to keep row 1 the same. So I'm going to write my system again. My system's going to be still here. Row 1, row 2 stay the same. I'm not changing anything there. I'm just doing one step here, and that's affecting row 3. So now row 1, row 3 will now have a negative on each of the values, and then I'm adding that to row 1. So notice, I'll have x plus a negative x. That's gone. I'll have y plus negative y. That's gone. I'll have negative z plus negative 4z. That will be a negative 5z. I will have 2 plus 3. That will give me 5. So notice, in actually just one step in this case, we eliminated 2 variables from the third row, from row 3. So we're actually very close, you might notice, to getting ourselves into triangular form. So when I think about what my second step will be, the second step needs to eliminate this x right here. That will be pretty straightforward because we have an x in our first row. So we can do something very similar to what we just did with row 1 and row 3. We can take row 1 and add a negative row 2. So that will give me, my row 1 is the same. My row 3 is also the same. I'll write that the same as well. But the only thing that is affected is my row 2. So when I have my row 2 is just going to have negative x minus 2y minus z minus 3. Every value just becomes negative, and then I'm adding that to my row 1. And that is my new row 2. So I have x plus a negative x, that's gone. So nothing here. I have y plus negative 2y, that will be a negative y. I have negative z plus negative z, so that will be minus 2z. And then I have 2 plus negative 3. So that will be negative 1. And then, like I said, my row 3 is the same. I have not affected row 3. But look at this. We now have triangular form. Our third row is just z. Our second row is y and z. Our first row, x, y, z. So now that we have this in triangular form, so we can make a note if we want, triangular form, where we did it. Now we can use that back substitution. So you're welcome to pause if you want and do what we did in the last example and back substitute, see if you can get the three values that we're looking for the solution to this system of equations. So I will start with solving for z. It's just a one-stepper. We get z equals -1. That allows us to then solve for y. We have -y minus 2z, z being a -1. That gives us -y plus 2, -1. Y equals -3, so y equals 3. And then last step would be to solve back up for that x. We will have x plus 3 minus z equals 2. So x plus 4 equals 2, or x equals -2. And then we put this into our solution here, which is -2, 3, -1. So that solution set there, that solution, -2, 3, -1, is those three values make every single one of those equations true. The left side would equal the right side if you plug them in. That's what makes it the solution.